What is multiprocessing and multitasking? There's a difference between multiprocessing and multitasking. Here, the ability to execute multiple processes simultaneously is referred as multiple processing. Systems which are capable of performing multiprocessing are known as multiprocessor system, which consists of multiple CPU. Okay, in this multiprocessing, we can tell that we will have multiple CPU, more than one CPU. So that if we have more than one CPU, what happens? Different processes can be executed at the same time. So that process is known as multiprocessing. Okay, now the ability of an operating system to have multiple programs in memory which are ready for the execution is referred as multi-programming. Okay, in case of multitasking, multi-programming is nothing but multiple programs will be executed at a time which has been ready in the execution. Whereas in multitasking, it refers to the ability of an operating system to hold multiple processes in a memory and switch the processor from executing one process to the other process. Okay, that is, in case of multitasking, you'll be having only one CPU. Okay, only one execution unit. Whereas in this particular multitasking approach, you'll get a feel that multiple CPUs are there, but actually one CPUs are there. Here, the entire task or the entire process will be in the ready queue, and uh, what to say, they will be continuous switching from task to task. From that means we feel that every task is being executed. My microprocessor, the controller will make sure that all the tasks are being executed one by one. Okay, but the switching is so speed that we feel that all the tasks are being executed parallel. So that is the basic major difference between multiprocessing and multitasking. Okay, so multitasking basically involves context switching, context saving, and context retrieval. Context switching in the sense, as I told you, multitasking, we have a single processor CPU, so therefore we will have to switch from task to task, right? So obviously, when switching from one task to other task, there will be certain registers or certain data that has to be stored. Okay, so that process is known as context switching or switching from one place to other place. And storing such data are known as context saving. And once the task execution is complete, if you want to come back to the previous task where the execution has stopped, that process is known as context retrieval. You need to get back the data where exactly the data of which has stopped its execution. So context switching, these are the three major concepts: context switching, context saving, and context retrieval in case of multitasking. So basically, there are different types of multitasking. So first one we call it as cooperative multitasking. Second one it is preemptive multitasking, and third one is non-preemptive multitasking. In cooperative multitasking, in the sense, this is also form of a preemptive multitasking in which task or a process get a chance to execute only when the currently executing task or process voluntarily goes off. Say one task is being executed. Okay, there may be different a number of tasks in a queue to be executed. So task which is in execution, if it voluntarily gives up all these resources, and if it makes a way for the execution of other task, then such type of task is known as cooperative multitasking. Whereas in preemptive multitasking, preemptive ensures that each and every task or process get a chance to execute. Okay, that is, each and every task should be executed. There is equal interval, equal time will be given for all the tasks. Or when high priority tasks come, there will be a preemption. So some strategies will be there, but in general, all the tasks in the queue will get an equal opportunity to execute to process. Okay. So when and how much time a process gets is dependent on the implementation of the preemptive scheduling. Okay, as the name itself indicates, preemptive in the sense it is going to uh, it is going to preempt the current running task, okay, and then give a chance to the other task which is in the queue. Other one is non-preemptive multitasking. In case of non-preemptive, in case of non-preemptive multitasking, here there will be no prevision. That is, process or task which is currently given with the CPU time, it is allowed to execute until it terminates. Okay, so whichever process has been executed, it will wait for the completion of that execution, and then after the completion only the next task will be given to the CPU. That is known as non-preemption. So these are the three major types of multitasking what we have in RTOS. So now we'll deal with different types of preemptive multitasking in this particular session. So before going forward, different types of preemptive multitasking, first we'll see what is task scheduling. Okay, what do you mean by task scheduling? In multitasking system, there should be some mechanism to place to share the CPU among the different tasks and to decide which process or the task is to be executed at a given point of time, right? That is, say during at a given point of time in a ready queue, there may be different tasks. Now the CPU, as we know that we have only one CPU, the CPU has to be shared. Okay, so that is nothing but sharing of the CPU with respect to the tasks which are in the ready queue is known as task scheduling. Okay, determining which task or a process is to be executed at a given point of time is known as task or process scheduling. Okay, so this is the basis of multitasking. So different scheduling policies are there which gives the guidelines for determining which task is to be executed. So we'll discuss all that in detail now. So in task scheduling, in that particular process, there are three main criteria to be considered. Okay, there are certain criteria to be considered to say that it is a good scheduler. Okay, so first one like CPU utilization time, throughput, turnaround time, waiting time, and response time. These are the five main criteria which we need to look into for a good scheduler. Okay, CPU utilization time. CPU utilization time is nothing but it is a scheduling algorithm. We should always make the CPU utilization as high. That is nothing but maximum number of times CPU should be utilized so that all the processes should be executed. So we need to make sure the scheduler should make sure that CPU utilization time is high. So it is a direct measure of how much percentage of CPU is being utilized. Next is a throughput. Throughput in the sense it gives an indication of number of processes executed per unit time. For a particular time interval, how many processes has been executed. That is nothing but a throughput. So therefore, throughput for a good scheduler should be always higher. Okay, turnaround time. Next criteria. What is turnaround time? It is a amount of time taken by a process for completing its execution. Okay, say once the process has come into the uh, uh, ready queue. Whenever it comes to the ready queue, basically it has to be copied to the main memory, and then from there to the CPU. All the resources should be executed, allotted, all that. That is, it includes the time spent by the process for waiting for the main memory, time spent in the ready queue, time spent on the completion of the IO operation, and the time spent in the execution. That is overall time starting from the what is that application of the task initiation, okay, till the end of the completion of that particular task. Okay, that time is known as turnaround time. And remember, the turnaround time should be minimum for a good scheduling algorithm. Okay, and next is waiting time. Waiting time in the sense, whenever the task is ready for its execution, it may have to wait for some resources, or it may have to wait for some for CPU. That waiting time is known as that is nothing but the waiting time. It is the amount of time spent by a process in the ready queue waiting to get the CPU time for the execution. So therefore, the waiting time should be minimal for a good scheduling algorithm. And the last one is a response time. Response time is nothing but it is a time elapsed between the submission of the process and the first response. Okay, submission of the process in this is the process in the whenever the process is placed in the ready queue and the and when the CPU gets that process. So that time is known as response time. For a good scheduler, again the response time should also be less. Therefore, we can looking at this slide, we can conclude that to summarize, a good scheduling algorithm should have always high CPU utilization, right? Minimum turnaround time, high throughput, maximum throughput, right? And minimum waiting time and low response time, that is least response time. So So these are the criteria which we need to look into when we schedule any or whenever the CPU has to be scheduled, or the scheduler algorithm need to look into this criteria. Okay. So coming to the task scheduling queues, basically there are three different types of queues in task scheduling. First one is job queue, ready queue, and device queue. Okay, a job queue in the sense it contains all the processes in the system. Okay, in order to execute the entire application, how many processes are there? The entire process will be in this job. Ready queue in the sense it contains all the process which is ready for the execution and waiting for the CPU. Okay, it has all the resources, all the other requirements are there, and it is in the ready queue. Only thing is it is waiting for the CPU to get its turn for execution. So that is known as ready queue. Okay, next is device queue. Device queue in the sense it contains a set of processes which are waiting for the IO devices. Okay, certain applications may require IO devices to complete this execution, and if the IO device is not available, okay, then execution cannot proceed. In that case, such type of process which is waiting for a particular IO devices will be in the device queue. Okay, this is about the queue, different types of queues in the task scheduling. So right now we have studied what is task scheduling, what are the criteria required for a good task scheduler, and also different types of queue in the task schedule. So this is the overall idea what we have studied till now. So you have a process, okay, job queue in the sense all the process of an application will be present here. This is nothing but the job, okay, and whenever process or particular process requires the execution, okay, and if all the resources are available, so such process will enter this ready queue. Ready queue in the sense it has all the requirements for the execution, only thing is it is waiting for the CPU for its scheduling. So here we'll have a scheduler algorithm. This clock indicates the scheduler algorithm which will pick up a particular process and send it to the CPU. Okay, so execution of that will contain, suppose if pre-emission is required, again it will be pre-emitted and placed in the ready queue. Pre-emission in the sense maybe based on certain criteria, if you want to execute some other process, then it has to stop the execution of the previous process and place it in the queue. That is known as pre-emission. Okay, and suppose if some certain CPU, if the IO devices are not available, then it will enter the device queue. Okay, it waits for the IO device. Okay, so this is the overall view of how this task scheduling takes. So we'll discuss some of the different types of scheduling techniques available in preemptive scheduling. Okay, preemptive scheduling. As I told you earlier, uh, this particular scheduling strategy will pre-emit the present running task based on certain conditions. Okay, based on certain conditions there will be pre-emission. So here every task in the ready queue gets a chance to execute. That is important. Every task in a ready queue will get a chance to execute. Okay, when and how often each process get a chance to execute, it depends on the type of the scheduling algorithm we are going to use. Okay, so scheduler can preempt the currently executing task and select any other task from the ready queue. When to preempt a task and which task is to be picked for the from the ready queue for execution after preempting the task is purely again depends on the scheduling algorithm. Okay, a task which is preempted by the scheduler, remember, task whichever is preempted by a scheduler, okay, it will go back to the ready queue itself. Okay, it will wait in the ready queue and it will wait for the CPU again. Once it gets the CPU, it will continue from the point where it has stopped its execution. It will not start from the beginning. Okay, where exactly the execution has been stopped, from that point the process will continue. Okay, so time-based preemption and priority-based preemption are the two important approaches adapted in preemptive scheduling. So under this scheduling, there are basically two types of approach. One is based on the time and other one is based on the priority. So we'll go to the first one, the first type of preemptive scheduling, that is known as SJF. Okay, shortest job first or shortest remaining time. Okay, either we call it as SJF or SRT. In general, it is shortest job first. So this is one type of preemptive scheduling algorithm. Here, in this particular shortest job first algorithm, in ready queue, it checks which which particular process has got the shortest time for execution. Okay, in a particular ready queue, the scheduler will check which process has got the shortest time for execution. So that process will be picked and then it will be executed. Okay, understood? That is the first point. Okay, picks the shortest execution time process. Once it is done, the next step is, okay, during execution, one more process will come to a queue. Okay, during the execution, if one more process comes to a queue, ready queue, and suppose if the execution time of that particular process, if it is less, okay, less than the present running task, then the pre-emission will occur. Right, understood? Suppose, I will repeat it. Suppose if we get one more process, okay, into the ready queue, which has the execution time lesser than that of the execution time of present running process. In that case, the pre-emission will occur. That is nothing but present running task will placed in the ready queue, and the one which has got the shortest execution time will go to the CPU for the execution. So this is about the shortest remaining time algorithm. We'll just go through the program. Possible you can work out. You can expect some problems under this particular topic. Say, example, we'll assume that there are three processes with process IDs P1, P2, and P3. Okay, there are process ID P1, P2, P3 with the estimated completion time as 10, 5, 7 milliseconds. Okay, which enters the ready queue together. So we have three processes, process 1, process 2, and process 3. Okay, it enters with the completion time, it is execution time as 10 of 10 millisecond for process 1, 5 millisecond for process 2, and 7 millisecond for process 3. Okay, fine, I'll stop here. Now we'll go to the solution. Now, in a queue, there are three processes. As per the shortest job scheduling, what it does is it selects the lowest execution time uh, process. In this, out of three process, 10, 5, 7, 5 is the lowest time required for the execution, 5 milliseconds, right? So therefore, process 2 will be executed, correct? Can you look at this timeline? You can observe here at 0, that is the initial state, process 2 will start the execution. Now it is given that a new process, P4, with an estimated completion time, that is execution time of 2 milliseconds, enters the ready queue after 2 milliseconds. Okay, one more process, that is P4, will enter the ready queue now, which has execution time of 2 milliseconds, and it enters that particular queue after 2 milliseconds. Now, at this, again observe this timeline. At second minute, after 2 milliseconds, okay, if I go to the ready queue, I have process 1, P1, process P2, which is been executing, process P3, as well as process P4. Okay, now the execution time of process P1 is 10 millisecond. Execution time of process P2 is already 2 seconds has been elapsed. So 5 minus 2 is 3. So execution time of P2 is 3. Execution time of P3 is 7 millisecond, whereas execution time of P4 is 2 millisecond. Right? So P4 2 millisecond, the execution time is very less. Therefore, the pre-emission will occur. That is, P2 execution of P2 will be stopped, and there will be a switching from the process P2 to P4. Okay, so P4 will be executed first, whereas the execution time is 2 milliseconds for P4. That is 2 plus 2 is 4. So till 4 time interval, this P4 execution will take place. After that, execution of P4 is complete. Now in the ready queue, I have three processes. Process P1 with time of 10 millisecond, process P2 with time of 3 millisecond, or because already 2 millisecond execution is complete, and process P3 with an execution of 7 milliseconds. Therefore, the smallest one is process P3 with an execution time interval left for 3 milliseconds. So P2 will be executed. 4 plus 3 is nothing but 7 milliseconds. So at 7 milliseconds, the execution of P2 is complete. Now in the ready queue, I have only two processes, process P1 with 10 milliseconds and process P3 with 7 milliseconds, out of which process P3 has got the less execution time. So P3 will start its execution. So 7 total time required is 7 milliseconds. 7 plus 7 is 14 milliseconds. 14 millisecond P3 execution is complete. Now in the ready queue, I will have only one process. I have one process, that is P1, with an execution time of 10 milliseconds. So 14 plus 10 is nothing but 24. So this is the overall timeline for the execution of all the four processes. Okay, and now based on this figure, we are supposed to find some values for waiting time as well as turnaround time. Okay, first say waiting time. We'll calculate waiting time. As I told you, what is waiting time? Waiting time is the time required for a process. Time required for a process to get the processor from the ready queue. Once that particular process enters the ready queue, from that particular time interval to the time required to the time where the CPU has been allotted for that process. Okay, that is nothing but waiting time. So first, if I calculate waiting time for P2, process P2, what is the waiting time for process P2? If I come back for process P2 has initially started its execution 0th interval itself, but at somewhere in between, one more process has come, right? P4. So here, 2 millisecond delay was there, right? So this is nothing but waiting time for P2. Therefore, 0, okay, plus 4 minus 2, you can neglect it, that is 2 milliseconds. So overall time is 2 milliseconds. Next, what is the waiting time for P4? If I come back again, P4 has come to the process ready queue after 2 milliseconds. Once it has come at ready queue, immediately the execution has started, right? So the waiting time for P4 is 0, right? It is given that a new process P4 with estimated completion time 2 milliseconds enters the ready queue only after 2 milliseconds. And it has come to the queue immediately, it has been processed because the time required for the execution of P4 is 2 milliseconds itself. Therefore, waiting time for P4 is 0 milliseconds. Next, waiting time for P3. So that directly you can write it looking at this table. So waiting time for P3 is 7 milliseconds. Similarly, waiting time for P1 is 14 milliseconds, right? So P1, P3 is 7 and P1 is 14. Calculate the average waiting time, that is add all this waiting time of P2 plus P4 plus P3 plus P1 divided by number of process, which is 4. You will get the average waiting time. Okay. Next, you are supposed to calculate the turnaround time. Now, what is this turnaround time? Okay, turnaround time is nothing but time spent in the ready queue plus execution. Okay, ready queue plus the execution time is nothing but turnaround time. So therefore, already you have found the time spent in ready queue. For P2, it is 2 millisecond. That is waiting time, right? That is nothing but time spent in the ready queue is nothing but the waiting time itself, plus the execution time of P2 is how much? It is 5. So 2 plus 5 is 7 milliseconds. Similarly, turnaround time for P4, waiting time is 0 and execution time for P4 is 2, therefore it is 2 milliseconds. Similarly, turnaround time for P3, waiting time is 7 milliseconds, execution time of P3 is also 7 milliseconds, so 7 plus 7, 14 milliseconds. Turnaround time for P1 is waiting time is 14 milliseconds and execution time was 10 milliseconds. So therefore 24 plus 10, sorry 14 plus 10, which is nothing but 24. And then find the average turnaround time, which is nothing but add all this divided by number of processes, which gives you the average turnaround time. Okay. Next concept is a round robin scheduling algorithm. In case of round robin scheduling, here, uh, as the name itself indicates, round robin, each process in the ready queue, okay, is executed for a predefined time slot. Okay, each process will be given a time slice. At every instant of the time slice, it will be executed, and after that, it will switch to the next process. Say, for example, in this particular diagram, you can observe if we assume there are four processes, okay, and if I assume the time slice is 2 milliseconds. So process one, initially it will pick the process one, the first one, whichever is in the ready queue, that will be picked, and it will be executed for 2 milliseconds. After 2 milliseconds, process one will enter the ready queue, and the scheduler will switch to the next process, process 2. It will execute process 2, and after 2 milliseconds, again process 2 will enter the ready queue, it executes process 3. Then again after 2 milliseconds, process 3 enters ready queue, process 4. and after 2 milliseconds again process 4 enters ready queue, next it process, it picks process 1. So this is nothing but round robin. Okay, in a circular fashion, at every time slice should be defined that for every time slice this will be executed. Okay. Similarly, we have an example for that. The same example, we'll assume that there are three processes. Okay, process P1, P2, and P3 with an estimated completion time of 6, 4, and 2 milliseconds. Okay, respectively, which enters the ready queue together in the order P1, P2, and P3. So you're supposed to calculate the waiting time, turnaround time for each process, and average waiting time and average turnaround time. We'll assume that RR algorithm uses a time slice of 2 milliseconds. Okay, so what happens first? The scheduler in this particular example, first the scheduler will pick P1. Okay, so P1 will now be picked at 0th interval. It executes for 2 milliseconds because it is given that time slice is 2 milliseconds. So executes P1 for 2 milliseconds. Okay, so what is the time interval left? 6 minus 2 is nothing but 4. Okay, 4 time unit interval is left for the execution. It shifts to the next process P2. Again, P2 will be executed for 2 milliseconds. So 2, okay, that is 2 plus 2, 4. Fourth interval, it will stop its execution. So P2 has executed for 2 milliseconds. So 4 minus 2 is. Next, it shifts to P3 process. P3 will be executed for 2 milliseconds. So 4 plus 2 is 6. At the sixth time interval, P3 execution will be stopped. And as we know that the execution time for P3 is 2 milliseconds, therefore 2 minus 2 is 0. P3 execution is complete now. And now at this particular instant, we have only two processes in the queue, that is process 1, P1, as well as process P2. P1 with a time interval of 4 and P2 with a time remaining of 2 milliseconds. Again, P1 will be executed for 2 time interval, and next there will be shift after 2 time interval. P2 will be executed again for 2 milliseconds. Okay, at this time interval, 10 time interval, the execution of P2 is complete. Okay, whereas in the queue I have only P1. Okay, process P1 with the execution time of 2 milliseconds remaining. So P1 will be executed again. By in the 12 millisecond, all the processes complete. Okay, now for the same table, for this particular time interval, you have to calculate the waiting time. So what is the waiting time for process P1? Waiting time is nothing but the time spent in the ready queue. So P1 here it is 0. Here it has to wait for 2 plus 2 4 milliseconds. So we as well as 2 more second over here. So total time is 6 millisecond, correct? Here it is 0. Here there are two processes. So 2 plus 2 it is 4 plus here 2 more seconds, so 6. So you can observe here waiting time for P1 is 6 milliseconds. Similarly, waiting time for P2. P2 initially 2 millisecond it has waited. Then after that here again 2 plus 2 it is 6. Similarly, waiting time for P3 2 plus 2 first 2 time interval that is 4 milliseconds. Right? So here 6 as well as 4 milliseconds. Calculate the average. After that, suppose if you want to calculate uh, turnaround time is nothing but the waiting time, the time spent in the ready queue plus the execution time. Right? So just add for P4, P1, execution time is 6, waiting time is also 6, 6 plus 6 is 12. Whereas for P2, execution time is 4, waiting time is 6, 6 plus 4 is 10. Whereas for P3, execution time is 2, waiting time is 4, so 2 plus 4 is 6. And calculate the average. This is about the round robin scheduling. Okay. So next type of scheduling is nothing but preemptive scheduling based on the priority. So here, looking at the priority, the pre-emission will take place. Okay, we'll consider the example. Uh, Whenever the process enters the queue, along with that, it will have its own priority. Okay, the one which has got the highest priority will execute. So the present, it checks the priority of the present running task. If the priority present in the ready queue is higher than the priority of the present running task, then obviously the pre-emission will take place and the execution of high priority task will occur. So here we'll consider the example. Three processes are there. Process IDs P1, P2, and P3 with an estimated completion time of 10, 5, 7 milliseconds. Okay, and priority is as for P1 1, for P2 it is 3, P3 it is 2. Okay, here 0 is the highest priority, whereas 3 is the lowest priority. Okay, 3 has got. Hello, am I audible? Am I audible? Hello? Yeah, here each priority will be assigned with a number. One as say 0 is the highest priority and 3 as lowest priority. So P1 is 1, next P2 it is 3, P3 it is 2. Therefore P1 highest priority in this particular example and P2 the mid priority, sorry P3 the mid and P2 the lowest priority, right? Which enters the ready queue. Now in ready queue I have P1, P2, P3 process. Okay, and also it is assumed that one more process, that is new process with an estimated completion time of 6 millisecond. Okay, the execution time of 6 millisecond and priority is 0. Since it is 0, it means that it has the highest priority and it will enter the ready queue after 5 millisecond of start of execution of P1. Okay, initially it will not be in the ready queue, that is process 4 will not be in the ready queue. Okay, it will enter the ready queue after 5 millisecond and it has got the highest priority, that is a 0. So we'll just go through it for this particular scenario. We'll go through it how the execution will occur. Okay, so first at the first end before the execution, P1, P2, P3, only 3 processes are in the queue. Okay, where the priority of P1 is 1 and P2 it is 3, P3 it is 2. Therefore the highest priority is P1, so P1 will be executed. So you can observe here P1 will be executing. So 0, 1, 2, 3, 4. At 5th millisecond it is given that it is told that at 5th millisecond one more process P4 will enter the ready queue, right? It will enter the ready queue and the priority of that is 0. Therefore 0 in the sense it has got the highest priority. Is it correct? Highest priority. So it comes as the present running task. Present running task is P1, priority is 1, whereas P4 the priority is 0. Therefore it has got the highest priority. So the present running task execution will be stopped. Okay, that is at 5th millisecond you can observe P1 execution will be stopped. P1 has been executed for 5 millisecond. What is the execution time of P1? Actually it should be 10 millisecond. Only 5 millisecond is over. It means that we have still 5 more millisecond to complete the execution of process P1. So it is stopped and P1 enters the ready queue now with the execution time left of 5 millisecond. P4 will start the execution because it has got the highest priority. So it will execute. What is the time required for the execution? It is given that it requires how much 6 millisecond, right? So 6 plus 5 it is nothing but 11 millisecond. So till 11 millisecond P4 will execute. At 11th millisecond the execution of P4 is complete. Okay, so P4 will be removed from the ready queue. Okay, then after that in ready queue you'll have only 3 processes after 11 millisecond, that is process 1, process 3, sorry process 1 with execution with the priority of 0, process 2 with the priority of 3 and process 3 with the priority of 2. So in that which is the lowest which is the highest, process 1 is the highest priority. So process 1 again it continues its execution. How many time is left? Already 5 millisecond it has completed its execution. So 10 minus 5 it is 5 millisecond. So it will execute for next 5 milliseconds. So 11 plus 5 is nothing but 16. Till 16 millisecond process P1 will be executed. Okay, next at 16th millisecond what will happen at 16th millisecond? At 16 millisecond at the ready queue you will have only 2 processes, that is process 2 and process 3, right? Process 2 with the priority of 3, process 3 with the priority of 2. So therefore process 3 has got the highest priority and process 3 will be executed from 16 time interval. What is the execution time for process 3? 7. So 16 plus 7 it is nothing but 23. Till 23rd time unit process 3 will be executed. At 23rd completion of process 3, so only one process is there in the ready queue which is nothing but P2. Okay, so it will be executed. So 23 plus 5 execution time is 5. So it is 28. 28 time unit, all the processes are completed as execution. So therefore, this is based on the priority, the execution will be processed. Okay, in the previous two cases, in the round robin as well as in the shortest job, it was based on the time of the execution, right? Whereas in round robin, time slice was here it is based on the priority. Now for the same thing, you need to calculate. I think you can do it later. Calculate the waiting time. Waiting time is nothing but the time spent in the ready queue. Okay, as well as you need to find the turnaround time. Turnaround time is nothing but the waiting time plus the execution time. Okay, so this is all about the scheduling, different scheduling uh, strategies in the preemptive technique. So any